Rise and shine, explorer! Day 8 has dawned upon us and has left us with no time to waste. Today, we're stepping up our game. We're going to add a dash of color to your monotonous existence by using a nifty piece of hardware called an RGB LED. Allow me to explain. RGB LED stands for red, green, blue, light-emitting diode. What this LED does is allow us to produce virtually any color on the spectrum by controlling the intensity of the 3 colored diodes. It's like your own personal rainbow producer. We're also going to cover a new function today, analog write. It allows us to send an analog output signal on a digital pin. Yes, I know what you're thinking. Didn't we just discuss how digital and analog are separate entities? We sure did. Let me, however, introduce you to the world of pulse width modulation, or PWM. This savvy little trick allows us to fake an analog output on a digital pin. Pretty neat, wouldn't you agree? Nonetheless, that's enough jabber for now. Rest assured, all this and more will be covered as the day progresses. Brace yourself in, explorer. We've got colors to mix and a spaceship to fix. An RGB LED is unlike your usual kind of LED, explorer. It's like a 3-in-1 special. Inside that tiny package, you'll find 3 separate LEDs, one red, one green, and one blue, as these are the primary colors of light. In a regular LED, you apply power and it emits a pre-programmed specific color. In an RGB LED, however, you have the ability to control each of the 3 colors individually. You can turn on the red LED, the green LED, the blue LED, or any combination of the 3. So, why is this exciting? Because by varying the intensity of each of these colors, you have the power to create virtually any color you want right at your fingertips. How deeply thrilling! Need a soothing aquamarine glow to relax? Easy. Want to flash a warning in bright alarming red? Ask and you shall receive. In essence, with an RGB LED, you're not just getting one color, you're getting the whole spectrum. Enjoy the possibilities, explorer. Okay, explorer, let's dig into 2 intertwined concepts, analog write and pulse width modulation, or PWM, which are critical for controlling our RGB LED. Analog write is a function in Arduino that helps us generate PWM signals. Despite its name, oddly enough, analog write doesn't really deal with analog signals. It's a bit of a misnomer, which could be a source of confusion. Have no fear, explorer. It'll all piece together soon enough. Moving on to PWM, pulse width modulation is a technique used to create a kind of fake analog effect using digital means. By rapidly switching a signal or power source on and off and changing the proportion of the time it is on versus the time it is off, we can vary the intensity of power that is received. This is important for our RGB LED because it allows us to control the intensity of each of the red, green, and blue LEDs, which in turn lets us mix our colors. Imagine PWM as a fast flickering light. If it flickers so fast that your eyes can't catch it turning on and off, the light will appear dimmer or brighter based on the ratio of on time versus off time. If it's on more than it's off, it appears brighter. If it's off more than it's on, it appears dimmer. In terms of our RGB LED, we'll use analog write to send PWM signals to each of the red, blue, and green LEDs. By changing the duty cycle of the PWM signal, that's the on time, we can control the brightness of each LED. By mixing different levels of brightness across the red, green, and blue LEDs, we'll create the color we want. You're in for quite a treat, explorer. The trajectory of your future will soon become a lot brighter. Quite literally. It appears we've talked the talk. Now let's walk the walk, explorer. Our task today is to light up our RGB LED and give it a whirl. Remember, with pulse width modulation, we can tinker with the intensity of each color, from a meager 0 to a dazzling 255. Talk about a spectrum. Now, one way to control our RGB LED would be to separately define the red, green, and blue values every single time we want to change a color. But frankly, that's like choosing to walk across the galaxy when you have a perfectly good spaceship. It's slow, and it'll leave your code looking like a debris field of supernova. Let's be smarter, shall we? What do you say we build a function to streamline the process? Something catchy and memorable like set RGB red level, green level, blue level. You'll see those 3 byte variables nestled inside the parentheses, separated by commas. These are parameters, and we'll be handing them over to our function like instructions to a well-trained robot butler. We don't have a lot of memory, so since max value doesn't need to be anything higher than 255 anyway, remember, pulse width modulation, a byte is perfect since its max value just so happens to be 255. Using something like an integer for an unsigned number less than or equal to 255 is just a waste of memory. Once we're inside the function, it's time to put those parameters to work. We'll use analog write to set the value for each of our 3 color pins. Efficient and tidy, just the way I like it. In our main loop, it's testing time. We'll call our snazzy new function in a variety of ways to make sure our RGB LED isn't just sitting there like a lump of plastic. Once we're confident everything's shipshape, we'll beam it up to our board and enjoy the show. Let's get to it, Explorer. Lights, camera, code. Now, for what you've been waiting oh so patiently for, let's turn to some instructional material that I was able to gather cached on the computer. I've also added this to your mission resources for future reference. See you soon.
Hello everybody and welcome back to day 8 of the code explanations for the 30 Days Lost in Space Adventure Kit. Today we're going to be introducing a couple of new concepts now that you have an RGB LED hopefully wired up on your breadboard. Today the concepts we're going to be introducing are going to be analog write and pulse width modulation, which allows us to give a variable intensity over a pin. And then we're also going to be looking into a new idea, which is yesterday we learned about functions, and today we're going to be learning about passing variables into said functions. And so with that, let's get started by first simply removing a few of these extra comments so that it's a little bit less daunting to look at. Explicitly, we included Arduino.h, but again, since we're using the Arduino IDE, if this was removed, it's not going to affect anything, so I'm just going to, for example's sake, completely delete it and show you that it still works. Next, we're going to define each of the pins on our RGB LED. Now, remember that the R stands for red, G stands for green, and B stands for blue. And all of these are pulse width modulation compatible, meaning if we send more intensity on that line, essentially sending more voltage onto it, we're going to light that red one either higher or lower, so we're going to get more red or less red, we're going to get more or less green, and we're going to get more or less blue. The pins that we're going to be using for this example are going to be 11, 10, and 9. Please note, however, that if you do change your pins, you have to be careful about it. On the hero board, only pins 3, 5, 6, 9, 10, and 11 support pulse width modulation, which is indicated on the board by preceding those pins with a tilde character, and only those pins can support pulse width modulation and use analog write. If you try to use any other pins, they will not work because those are digital pins and they do not support pulse width modulation. Once we're done defining our pin outs, we're going to go down and we're going to define a set of constants to represent 4 different brightness levels for our RGB LED using pulse width modulation pins and analog write. Pulse width modulation can set values ranging from anywhere from 0 to 255, which we will simply demonstrate by adding 64, or approximately 1/4 of that range, to each preceding value. So we can start by saying that off is essentially the equivalent of a value of 0. Then we can say that dim is maybe something like 64. Brighter is going to be 64 plus dim, which is 64. So this would be about 128. So as you can see, we're getting a little bit higher and higher and higher up until we reach 255. And we're going about 1/4 each time. So we have dim, brighter, bright, and brightest. And each time we just go a little bit higher than the last one. Next, we have another constant down below. And this constant is simply just going to say how long we want to display each color. And we're going to change this as a global variable, so if we ever want to change it in the future, we can change it in one spot instead of a bazillion places down below. So if we wanted to change it to 1 second, we can do that here or whatever, but I'm going to keep it 500 just for example purposes. Now we're going to hop down to setup, and as you know, setup is pretty similar to every other day. We're just going to be simply setting all of these pins as outputs. And that's it. We're not going to be reading off a serial monitor today, unless of course you want to for any debugging purposes, but for our purposes, we can remove that and we don't have to worry about it for right now. Then once setup is completed, you guessed it, we go straight to loop. That is simply how the Arduino language works. Now, before I get into everything that's going on in loop, let me just tell you a general gist of what this is doing, because I do need to explain one other thing first. Right here, we're simply showing, and we're just kind of rotating through various colors, and we're rotating through them in a way that allows us to turn red, green, and blue and show off how pulse width modulation actually works. That's kind of the point of this program. But you'll notice that there's a function being called in a lot of places called display color. This is not one that was built into the Arduino IDE. This is not one that is given to us by default. This is a function that we actually have defined ourselves below. Display color is a function that accepts 3 parameters representing the desired intensity for each of the LEDs in the RGB LED. So display color is a very shorthanded way of saying what color we want to set it to by setting the red intensity, the green intensity, and the blue intensity. That allows us to display almost any color in existence by simply having those 3 at a certain variable, and you can have them anywhere from 0 to 255. The way that this is written is exactly the same as yesterday. We have a void, because it's not going to be returning anything. It's simply just going to be executing display color, and the difference is inside of these parentheses we have parameters. This is a new concept for today. We have parameters, and we have the red intensity, the green intensity, and the blue intensity. And these can be anywhere from 0 to 255, and they're separated by commas. Now, I want to reiterate that this can actually be changed in terms of how this is written. The reason it was written on multiple lines is simply because our ability or our desire to add comments so that you can understand what everything is going on made it so. So let's actually just quickly go like this, and I can show you that you can actually do this all on one line. And personally, if you weren't commenting everything, I'd prefer it to all be on one line. And here, it's a little bit cleaner. So, void display color, red, comma, green intensity, comma, blue intensity. So you need to have all of these. Every single time you call this function, you need to send in 3 parameters, and that would be what you want to set red, green, and blue to. Then, when it hops into the function, we're going to simply do another function called analog write. I'm sure you've heard of analog read. Well, analog write is the exact same as instead of reading off of a pin, we're going to be writing to a pin. But we're not going to be writing whether it's on or off. We're going to be writing how on or how off we want it to be. In this case, we're going to be setting red to a number between 0 and 255, green to a number between 0 and 255, and blue to a number between 0 and 255. And we do this every time we display the color. Now, if we want to do that, we can go up here and we can show exactly us doing that. Let's first display the color is off, off, and off. This is setting all 3, red, green, and blue to 0, 0, 0. This will turn our RGB LED off. We won't be displaying anything on there at all. Next, we're going to delay by half a second, which is what we've defined up here as color delay. Then we're going to set the red to dim, and we're going to keep green and blue off. Then we're going to delay by that same time, and then we're going to set red to brighter, and again keep everything off. Then we're going to delay, send a little bit more voltage to red, and then we're going to delay and send a little bit more voltage on that red line right here at the brightest, where we displayed at full intensity at the end. The reason we're doing this here is we're going to be demonstrating how pulse width modulation can work. you can send a whole variety of different signals on the same exact pin using analog write down here, and it can display a whole different variety of different values. This is really, really helpful in cases like this where we want to have various versions of red, or maybe just some different colors. Maybe you need more red and less blue, or more green and less red for various different colors on the color spectrum to help us display a whole variety of colors. Next, after we're done showing off how pulse width modulation works using the red LED, we're going to display our other two LED colors at half intensity. We'll first flash on the green LED, and then we'll flash on the blue LED. So you can see that those are also there and working. Finally, we'll hop down to show a bunch of various colors. For example, you can display yellow by mixing red and green LEDs. Bright, bright. You can display cyan by mixing the green and blue LEDs and keeping red off. And then you can also display magenta by doing red and blue. And of course, keeping green completely off. Finally, if we display everything at once, bright, 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 you'll get this color of white. And that's simply science and how light works. So with that, we should have a completed simulation of how pulse width modulation works using the RGB LED, and how you can set up a whole variety of different colors using just very, very simple amounts of code. So with that, that should be about the end of our code explanation for day 8. I will see you again tomorrow.
Welcome to the Day 8 wiring example video. In today's project, we'll introduce a new component and a new programming method. The new component is a 3-color red, green, blue, or RGB LED. And the new method that we'll use to control it is called pulse width modulation, or PWM for short. Let's dive into today's circuit and see how these things actually work. We have a 3-color LED right here, just for us to look at. And we have another one that's actually plugged into the circuit on our breadboard. We can see just by looking at it that the 3-color LED is different from the conventional LEDs that we've used so far. The 3-color LED has 4 leads instead of 2. And you'll notice that one of the leads is longer than the others. This one right here is longer than the others. And that one long lead serves as the ground connection for all 3 colors that are incorporated into the RGB LED. The remaining 3 shorter leads provide the positive connections for the red, green, and blue channels. And you may notice that this is actually a reversal of our usual convention in which the long lead of the LED is the positive one. Well, it's backwards here, and we're just going to have to get used to this inconsistency. As a matter of fact, to make things even worse, sometimes you may get a color LED in which the long common lead is positive rather than ground. And if you happen to get one of these so-called common anode LEDs, you'll need to use an alternate circuit and sketch design that reverses the direction of current flow so that the LED will function properly. But for now, we'll focus on what we have here. In our circuit here, we see that the LED's 3 positive leads are each fed by the hero from a separate pin, a separate digital pin on the hero. In this case, we have our 3 channels, the red channel, the green channel, and the blue channel, fed by these 3 pins right here. Blue is 9, green is 10, and red is 11. Now, one of our goals in this project will be to control the relative brightness of the 3 colors. But at first glance, it would seem that using digital output pins would be a bad choice for this job, since a digital output is either on or off. It's not an analog output. But it turns out that pins 9, 10, and 11 are 3 of the special output pins that can be programmed with pulse width modulation. That is, they can be programmed to rapidly pulse on and off, with the fraction of the time spent on determining how bright the perceived light is. So for example, if we programmed the pulse width such that it was on half the time and off half the time, that would give us a 50% brightness, and so on for other brightness levels. Now, the rest of our circuit here should be fairly familiar to us by now. We have 3 220 ohm current limiting resistors, one for each of the 3 color channels, the red, green, and blue. And we also have a single black wire right here, which connects from the ground pin of the LED up to the hero ground, completing our circuit. So this is all relatively straightforward for us. And so the next thing for us to do is to run the Day 8 sketch to demonstrate how these features work together. Now, before we actually run it, let's read through the sketch and see what is expected to happen. If we look through the sketch, we immediately see that the loop function is repeatedly illuminating the 3 channels in a specific sequence. First, in the loop function, we see that only the red channels turned on at 25%. Then, after a time delay, that is increased to 50% on red, followed then by 75%, and then finally full illumination or 100% on the red channel. Next in the sequence inside the loop function, we turn off the red channel and turn on the green at 50%. So we'll look for that. Following the green illumination, then we turn that off and turn on blue at 50%. So we should expect to see red followed by green followed by blue. Next in the sequence, we're going to demonstrate the ability to produce other colors by mixing different amounts of RGB. So in our next step in the sequence, we display yellow by turning on red and green at 50%. After another delay, we next produce cyan with equal amounts of green and blue. And then we produce magenta. Magenta is displayed with a mix of red and blue channels on our LED. Finally, to conclude the loop function, we turn on all 3 LEDs together at 100%, and that should produce a bright white light. This sequence then will repeat as the loop function runs over and over as long as our sketch continues to run. So at this point, since we know what to expect, let's go ahead, upload the sketch, and watch to see that the sequence is executed as we expect. For this demo, I've set the color delay time to 1500 milliseconds, or 1.5 seconds. So hopefully that'll give us enough time to be able to see all the steps of the sequence as they execute. So uploading now, we should look for the red LED to come on. There it is. Dim, brighter, brighter yet, and brightest. Followed by green. There's our blue. There's yellow. There's cyan. There's magenta. And finally, bright white. Then the cycle just repeats over and over again. And so we can watch this go through its cycle as often as we want. That just about covers all the new ideas that we've introduced for today's project. But you might want to experiment with some of the sketch parameters. For example, you might want to see how good you are at producing other colors or produce different timing effects. Have fun with this, and next time we'll see how to use our newly acquired knowledge to further contribute to our repair mission.
Well, Explorer, I must say I'm impressed. You've wired up the RGB LED and successfully programmed it to show different colors based on given values. Your code is no longer a maze of repeated color values. It's streamlined and efficient, like the inner workings of a cutting-edge spaceship. and our hero board is sparkling with colors. Just the kind of bright glimmer of hope you need in the depths of an underwater world. Now, don't get too cozy in your success. Tomorrow, we'll take another momentous leap forward. I see a dashboard display in our future. It's time to start getting some visual feedback from our various ship systems on a display. Yes, indeed. Just because we're marooned in an alien sea doesn't mean we can't have a bit of style, right? So, rest up, Explorer. We have many more lines of code to write and much more hardware to wrangle before our ship can once again break free from this watery prison. But for now, bask in the glory of your multicolored triumph. Tomorrow awaits.